So let's go back to the PowerPoint. And so we talked about why it's important to randomize. Now I want to get into blocking. You just saw me talking about blocking or randomizing within groups. Blocking is used to remove identifiable sources of variation in the experimental subject or setup. Excuse me. You know, if you're on a slope, on a hillside, that is a source of variation. The amount of moisture at the top of the slope and the bottom of the slope are different. Maybe even sunlight might be a little different. So randomizing isn't enough, and you want to group things in different strata or blocks. Now, stratification isn't something we talk about in statistics unless you're in an advanced statistics class usually. We usually just use the term blocking. So even if a field doesn't have a noticeable slope, so bean seeds planted in a field with a noticeable slope, there are gradual differences in the soil moisture, soil pH, soil nutrients, and light intensity on that slope. But even what we consider flat ground, out here in Salinas, we grow a lot of our crops in flat ground, don't we? No, we don't. It's not really flat. There is a small slope of just 1 or 2% or something that is important, because 1% means for every 100 feet I go down the row or down the grade, I drop a foot in elevation. So if I have a 400-foot row and I have a 1% slope, really flat, the top of the field is 4 feet higher than the bottom of the field. Do you think there's going to be difference in how water responds to gravity? 4 feet higher on one end, 4 feet lower on the other. The top of the field and the bottom of the field, even when you see it as flat, you think it's flat. It's not. And that can be quite distinctly different. And you might not notice those differences when you're walking by, driving by. But you spend years dealing with certain crops in certain fields, and you'll start to notice there are patterns, there are trends, things you can see where the plants look different at the top of the field versus the bottom of the field, the high point of the field versus the low point of the field, even if those differences are only 1% slope. So you need to take that into account. You need to block. So here's a Christmas tree experiment. Here's the slope. So you've got a row of trees. Now, if you look at the mouse going back and forth on these top 4 plants at the top of the slope, imagine these are all at the same elevation. This is not going up the hill even further. So there's 4 rows at the top of the slope, or 4 trees, excuse me, at the top of the slope, 4 trees at the second level, 4 trees at the third level, and then 4 trees at the bottom of the slope. All right. So you always want to block or group your experimental subjects so they are in the same condition. And you do that by blocking perpendicular to the environmental gradient. In this case, the environmental gradient is the slope going down the slope. So you block perpendicular or across the slope. Now, if we look at this, is that a good experimental design? The block 1, we're just scattered. We're just selecting plants at random. I've got the purple plants are all around up here just randomly. And there's more plants at the top of the slope. The yellow ones have more plants at the bottom of the slope. The bluish ones are kind of all through the slope. It's just not a good way to block. There's no pattern or consistency within the blocks. It's just random. And this would be considered something that would be a completely randomized design. You might do this at times, but I'm not going to even get into that. That's different than blocking, and it gets confusing. That's a topic for another class. What about this? They're all going down the slope. Hey, every block has a plant at the top. the top middle, the bottom middle, and the bottom. So every block is homogeneous. Yay. No, boo, actually, because what we're trying to get at is a measure of the variation caused by the slope. And unfortunately, with these different groupings, with these different groupings, let's take the yellow block 4, for example. I've got one plant at the top, one plant at the bottom, and 2 plants in the middle, and I can't measure the differences. But what if I have this? Now the slope is going down the hill, the environmental gradient is going down the hill, but my blocks are going perpendicular to the slope. They're going across the slope at a 90-degree angle to that slope. Now I've got a group of plants all at the top of the hill, and they're comparable. They're a block, they're a group. They're all in the same environmental situation, the top of the hill. So they make a block. Now I've got ones that are just below the top, block 2. They're all in the same situation. Block 3, again, they're near the bottom, but not at the bottom. They're all the same. And block 4, they're all the same. So I can get a measure on my environmental gradient caused by the slope, my experimental error potentially caused by the slope, by getting the average of block 1, comparing it to the average of block 2, comparing it to the average of block 3, and comparing it to the average of block 4. And that's a hard comparison to make. That's where analysis of variance comes in. That's where, you know, you let a computer do the work, or you spend a lot of time on paper. All the first analysis of variance I did, we had to do them by hand on, you know, pencil and paper. And it took sometimes days to do the analysis of variance and recheck it and recheck it till we came up with the same number 3 times. Then we know we're confident in our data. But with a computer, you plug in the data and it can tell you something about how much variation is being introduced or error is being introduced based on the slope of your location, your experimental site. But now it's time to apply treatments. So if I have a block, here's my block 3 or whatever it is, I don't care. Now I apply my treatments, treatment 1, treatment 2, treatment 3, treatment 4, and the treatments have been randomized within my block. So within each block, I have randomized my treatments. So here is my trees in a block. Let's say I just called these trees 1, 2, and 3, and I've randomized the treatment. So now tree 1 gets treatment A, tree 2 gets treatment C, and tree 3 gets treatment B. That's where this spreadsheet comes in handy. And so here you've got your trees, and you can just assign them the treatment based on what Excel's random function tells you. And now here's my final properly randomized, blocked, or stratified experiment. I've got my purple block 1, my green block 2, my bluish block 3, and my yellow block 4. Every one of the blocks has all 4 of the treatments: the solid color, the coarse checkered color, the grayed color, or the lightened color, and the fine checkered color. If you look at that, they all have the 4 different treatments. There's my experiment on my Christmas tree farm. I've got 4 blocks and 4 treatments. And actually, I've got 4 blocks, 3 treatments, and a control. One of those treatments is my control. Here's another example. I talked about this already. If I've got the top of the field and the bottom of the field, where is water most likely to go? The bottom of the field. Even if you don't get more water actually running down to the bottom of the field, if you just look at where the water table levels off under the soil, it's still going to be at the bottom of the field down here. The plants are 4, 5, 6 feet lower, and so they're going to be more likely near more water, more likely. Every field is different. This doesn't always hold true. There can be all kinds of things that go into your particular field or block, and you got to look around. I've had blocks where there are natural springs that come up in part of the field. Stay away from that block, or stay away from that side of the block. When I say block, I'm thinking planting block, like 40 acres, not an experimental block. I should, again, be careful. There's words used different ways. We have block in our experimental unit, which is a small group in our experiment, and my more casual use of the word block. If you're out there in the vineyard, what do? You've got different blocks in your vineyard, right? But those are 1 to 20 acre chunks of your vineyard, all with the same variety of scion and rootstock, all with the same irrigation unit. So in vineyards, you can call them irrigation units, possibly, to avoid using the word block when you're talking statistics. Anyway, you've got a problem. So the noise, the changes in your treatment effects, the amount of change in the dependent variable, the things you're going to measure, can be messed up with the changes in the soil moisture, which isn't supposed to be part of your experiment. So you block against it. If I go parallel to the moisture gradient, every block is all mixed up. I've got dry areas and wet areas, and all of my moisture effects are confounded in the blocks, or mixed up in my blocks. However, if I lay out my experimental design with my blocks laid out perpendicular to the identifiable environmental gradient, in this case, the identifiable moisture effect, or top of the field versus the bottom of the field, now this top block, block 1, is all at the top of the field. Block 2 is all, 1 step down. Block 3 is 2 steps down. Block 4 is at the bottom of the field. Now, I would never go to the top and the bottom. Actually, my general rule of thumb for most experiments in lettuce or spinach was just try to burn 50 feet off the edge of the field. If I'm running a smaller experiment, I burn the first 50 feet on either end, and I run my experiment in the middle. Do I need 50 feet? That's probably a little bit of overkill, but that way I don't have any problems of being too close to the irrigation source. I don't have any problems with being too close to the roadways or other possible sources of environmental error. You never want to be near the edge of a field or an irrigation unit at all, if at all possible. But this is an ideal experimental randomized complete block design. It's a blocked design because I have 4 blocks. It's a complete design because if I look at this, every single one of these blocks has treatment 1 through treatment 5, with treatment 1 probably being my control treatment, or my control groups. T1, T2, T3, T4, T5, T1, T2, T3, T3, T4, T5. And it's randomized. All of them are there. It's complete, and all of them are randomized. So block 1 is randomized separately from block 2, which is randomized separately from block 3 and separately from block 4. They are each randomized independently of each other. And now I have myself a good field layout for an experimental test using a randomized complete block design. So I need to take another break because this is a little longer one.